Alright, in this problem it says a piece of sodium is illuminated with light of wavelength 700 nanometers. If the work function of the metal is given in this many electron volts, will electrons be emitted? So I drew a picture of a slab standing for the sodium metal. And you might remember from chemistry that sodium has one electron in its outer shell. So my guess is it's going to be easier to dig out an electron from sodium than it might be from a slab of a different kind of metal. But it says that we are using light that has a wavelength of 700 nanometers. 700 nanometers might be considered like a red light, maybe borderline infrared. And I don't have a red pen here, so I'll use pink. Alright, so here is going to be my wavelength, my light ray, that has a wavelength of 700 nanometers. They also tell us that the work function, which is the amount of joules that I'm going to have to spend to get the electron out, so the work function is given as 1.7735 electron volts. So that's just a common unit of energy in this topic, but I need to convert that value to joules. So I'm going to go into my calculator energy conversion menu and put in 1.7735, and I'm going to turn that electron volts into joules. And that is equal to 2.84 to the negative 19. So let's write that down. 2.84 times 10 to the negative 19 joules. So that's how many joules is needed to dig out the electron. Then the question is, what is the energy of our incoming light? So I'm going to write that here. E equals HF. So H is Planck's constant. So that's going to be 6.63 times 10 to the negative 34 times the frequency of the light. But we don't know the frequency of the light, we only know the wavelength. So I can go over here and I can use the wave equation, which is C equals frequency times wavelength. And all of the waves of the electromagnetic spectrum travel at the speed of light, so I can put that down, 3 times 10 to the 8th. I'm looking for the frequency, and I have a wavelength of 700, but that wavelength needs to be in meters, and I have nanometers, so that would be times 10 to the negative 9. So I can solve for the frequency, and I did that, and I got 4.29 times 10 to the 14th, and that would be hertz. So I'm going to take that value now, and I'm going to plug that frequency in right here, 4.29 times 10 to the 14th hertz. So how many joules of incoming energy do I have? So I'm going to take those values, 6.63 to the negative 34 times 4.29 to the 14th, and I get 2.84 times 10 to the negative 19 joules. So you can see I kind of rounded off there a little bit. So Einstein came up with a relationship that says if you wanted to know the kinetic energy of the released electrons, you take your incoming energy, HF, that's actually this value because we already multiplied the HF, and then you subtract off the joules that you have to spend to dig the electron out, which is the work function. So obviously I have 2.84 times 10 to the negative 19, that's my incoming energy, minus my work function, which is 2.84 times 10 to the negative 18, and we find out that we have 0 joules left over. So we did get an electron to come out though, so I'm going to write an electron here. Because this was my incoming energy, 2.84 to the negative 19, it took 2.84 to the negative 19 to get the electron out. He just does not have any kinetic energy. So I'll write down kinetic energy is 0. And if his kinetic energy is 0, his velocity is 0. So that might have been one way that you did this problem, and that might be an answer that you got. But I want to show you something else, so I'm just going to put a line here. So sometimes we end up arguing with our neighbor in terms of who's right and who's wrong. Because if you had started the problem like this, and you wrote down the equation for the photoelectric effect, and you wrote down the same values, Planck's constant to the negative 34. We take our frequency value that we got here times 10 to the 14th, and then we subtract our work function, which is 2.84 times 10 to the negative 19. And if I do this whole thing in my calculator, where I'm kind of putting like a bracket around these kinds of things, I minimize my round-off error. And this round-off error actually becomes very significant in a problem like this. So let's do that again. So I'm going to parenthesis my 6.63 to the negative 34. So this is my incoming energy. So HF, so times 4.29 to the 14. And then I'm going to subtract off my work function, which is 2.84 to the negative 19. And when I did it above, I got a 0, but this time I didn't get a 0 because my calculator kept the round-off error to a minimum, and I find out that the kinetic energy actually is very close to 0, to the negative 22 power, that many joules. And you might take something to the negative 22 power and you say, okay, that is approximately 0, and that would be okay. Somebody else might say, oh, no, I have kinetic energy. And then you might take that kinetic energy and plug it in the kinetic energy equation. And let's go with that for a minute. So I'll take 4.27 times 10 to the negative 22 is 1/2. And since we're talking about an electron, I'm going to plug in the mass of an electron, which is 9.1 times 10 to the negative 31. And then v squared. And so now I'm going to solve for v. So I'm going to take that value here. I'll multiply both sides of the equation by 2. And then I have to divide by the mass of the electron. And that would be equal to v squared. And then I'm going to square root the v. And I get an answer of that electron that I thought had no velocity has a velocity of 30,634 meters per second. So obviously that's a very different answer than 0, but it's all in the scheme of a round-off error in your calculator. So it would be appropriate if you said that he doesn't have any kinetic energy and his velocity is 0. It would also be appropriate if you said that he does have kinetic energy and his velocity is 30,000. Okay, I hope that helped.